Hi, everyone. Welcome to the 38th online Spintronics seminar. Thank you for joining us. This is Xin Fan from University of Denver. It's my great pleasure to introduce our speaker today. Dr. Fei Xue got his bachelor degree from Nanjing University in China in 2012 and a PhD degree from UT Austin in 2018. His thesis work is focused on interactions and topology in two-dimensional semiconductors and semi-metal under the supervision of Dr. Alan MacDonald. He is currently a postdoc at UMD NIST, working with Dr. Paul Haney. His research interests include spin-orbit coupled quantum transport phenomena and interaction-induced novel phases and collective excitations in low-dimensional quantum materials. So without further ado, Fei, please take it from here.
Yeah, thank you so much for the introduction, and thanks Xin and Creo to organize this wonderful seminar series. We all learn a lot in this special pandemic time. At least I listen every episode after I got the invitation from Xin to about these seminar opportunities. And so I'm very happy to talk about our recent work on this spin-orbit torque, especially this unconventional form of spin-orbit torque in the crystal with reduced symmetry. This is a collaboration work with Dr. Paul Haney at NIST. So this is, I'm a postdoc employed by University of Maryland. So I want to acknowledge the funding support. So before I go to any details, let me take a snapshot of the bilayer geometry I will talk about throughout the talk again and again. So here is a conventional bilayer structure we study in the spin-orbit torque. So we have a substrate, normally is a non-magnetic heavy metal such as platinum. And on top of that, we have a ferromagnet. It can be Permalloy or cobalt or any other ferromagnets. And in this bilayer structure, we know that even with simple symmetry analysis, we know that when we apply electric field, we can induce a torque on the ferromagnets. So in this talk, we will focus on another kind of substrate in the sense that in this substrate is still a one material. It's not a heterostructure implant. It's a one material. The color just indicates that this material breaks the implant symmetry compared to the conventional heavy metal one. So now let's jump into this takeaway from this talk. So there are three important messages I want to convey in this talk. The first one is we demonstrate that in the first principle calculation, there can be a considerable out-of-plane dampinglike spin-orbit torque generated in the crystal. For example, the example we use here is 1T prime tungsten ditelluride. So this is, again, the geometry is showing here. In this tungsten ditelluride, because of the implant symmetry breaking, we are allowed to generate a torque. This is a specific, it's a dampinglike torque, even when the magnetization lies along the high symmetry direction Y here. It is not allowed in the conventional platinum cobalt, for example, because of the symmetry. And also there are two, I think there are even more, but these two are directly related previous seminars in this online series. You can look for the time, here is the time and the speaker name. You can look for their talk. And I will probably skip some of details because of the previous ones. And the other takeaway is not just a calculation of the torque or the dependence or behavior of torque itself, is we are trying to understand why such a torque exists and how this torque is coming from. So our conclusion, at least in this heterostructure we have studied, the source of this spin-orbit torque is quite conventional in the sense that spin current flow from the substrate to ferromagnets is the major source of this spin-orbit torque, even for this unconventional perpendicular out-of-plane torque. There are also many related talks. These three are most related. Please check them out from the theory point. And the last one is motivated by the finding in the first principle calculations that the spin current contributes to the torque. And we want to simplify the picture even more without worrying about all these heterostructure details. It's a pain to actually get these heterostructures and also trying to model them. What about if we can only consider a bulk of this substrate, for example, tungsten ditelluride? Can we still understand the spin current flux generation in that bulk limit? And the answer is we can still do that, but we need some of twist layer to do that. We will talk about that later. So now let's go to the overview very quickly. So all the spintronics phenomena, from my understanding, is angular momentum flow between different angular momentum reservoirs in the solid state crystal. So we have this kinetic energy in the crystal. We also have this crystal field coupling between the electron atomic orbital and the crystal lattice. And we have this magnetic spin exchange coupling due to the magnetization, which is actually the interaction effect. And because of the relativistic effect of electrons, we also have spin-orbit coupling. Here is just one form of atomic on-site spin-orbit coupling, but there are other forms also in the general. But the thing is, all these terms tell us that we have different angular momentum reservoirs in the solid state system. Magnetization, spin, orbital, lattice, angular momentum reservoirs. And there are flows between different angular momentum reservoirs due to this coupling I talked about earlier. So this is a little bit too complicated, at least for me. So let's simplify things a little bit. So if we consider the ferromagnets, where the exchange coupling is the dominant interaction, and we can ignore the crystal field, we can ignore the spin-orbit coupling in the ferromagnets. So we only have kinetic energy and spin magnetization exchange coupling. In that case, the diagram simplifies a lot. We only have two reservoirs left. So we have this exchange interaction between the magnetization and the spin, that's all. So even with these two, we can come up with something very interesting and classical. It's so-called spin transfer torque. So here is the geometry. We have this tri-layer system. We have a fixed layer of ferromagnets and the free layer of ferromagnets. The important thing is the ferromagnetization magnetization angular momentum are not aligned with each other. So it's a non-collinear configuration. And there's a spacer, it can be normal metal or insulator. So now if we apply a charge current through this tri-layer, it's also called a magnetic tunneling junction. So when the charge current passing through the first fixed layer, it becomes spin polarized because of the exchange interaction. And then this spin current and the charge current together in the spacer passing the second layer, and will also become spin polarized, but it will change the spin polarization direction due to the non-collinear direction of M1 and M2. So now we can do this angular momentum conservation steady state calculation. We know from simple algebra, there is a net angular momentum change when the electron passing through the second layer. When there's an action, there's a reaction, which means that M2 also must observe this change of angular momentum. So with that effect, the M1, the M2 will flip, will change the magnetization direction, and also the spin current passing through the second layer will go with them. So this is the idea of the spin transfer torque. And with spin transfer torque and this so-called TMR, tunneling magnetoresistance, we can already build something very useful in the industry. It's called a spin transfer torque based non-volatile memory. So it's what we just discussed before. The spin transfer torque is the writing mechanism for this magnetic tunneling junction, where we apply a current passing through the magnetic tunneling junction. We can change the magnetization direction of the free layer. So we can write them down as 0 or 1. And for the reading, we use the same geometry. We know that from the, similar to GMR, we know that there's a large resistance difference when the spins in the top layer and free layer and the fixed layer are parallel or anti-parallel. So with that, we can do the writing and reading. So this is a memory. It's already actually in the real world application. I think Samsung already shipped out some of them, maybe 1 year or 2 years ago. So there is a small problem for this device. The thing is, when we do the reading, we apply a perpendicular current through the tunneling junction. When we do writing, we also need a current passing through along the same path. This means that when we do this reading and writing a lot of times, more than 1 billion times, it will not become as reliable as the initial condition, and especially this spacer is manganese oxide. They can be destroyed after so many operations. So there's a problem with this, is the reliability for the real application. So we already see that the important thing is to get the spin current passing through this tunneling junction with non-collinear spin direction, so we can flip the magnetization direction. And we know that in the solids, we have other angular momentum reservoirs. And how about this reservoir? Can this reservoir also generate a spin current? The answer is yes. So there's so now we ignore the magnetization. We consider a non-magnet heavy metal, for example, because we want a large spin decoupling here. So with the spin decoupling crystal field potential, we can get a spin Hall effect in the non-magnetic system. So spin Hall effect is very similar to the anomalous Hall effect, which is well studied and even discovered more than 100 years ago. So the spin Hall effect has this schematic description here. I draw here. So when we apply a charge current, there is a spin current flow also excited by this charge current going everywhere perpendicular to the current direction. And the spin polarization or spin direction is perpendicular to both the spin current flow direction and the electrical charge current flow direction. So this is an anti-symmetric tensor form of this spin current conductivity. And this spin Hall effect has been experimentally verified more than 15 years ago in this paper. In their experiments, they use doped gardner arsenide samples to see that there's a finite spin accumulation in the edge of the samples, and at different edge we have opposite spin accumulations. And by the way, the spin Hall effect, the spin current itself, you can calculate this spin current conductivity, but this conductivity itself is not something we can measure directly. We can only measure the consequence of this spin current, which is the spin accumulation in this case. And also in the next slide, we will show that this consequence of the spin current can also induce a torque. So now if we combine the spin Hall effect in a heavy metal and the spin transfer torque idea of this magnetic tunneling junction, we can achieve so-called spin orbit torque. This will be our main focus in this talk. Let's remind ourselves this classical first series of experimental paper from Cornell group. So when we apply input electric field, this is a key difference compared to the spin transfer torque, where you have to apply the current in the perpendicular direction. So when we apply input electric field, we know that there's a spin Hall effect generating the spin current flow in the Z direction, and the spin direction is in the Y direction. Now the spin current flux into the free layer will try to flip the magnetization when they are not aligned. So in this way, we change the magnetic tunneling junction from anti-parallel to parallel, so we can read out the using the TMR, we can read out the signal, so we can see that we have a different signal when we do the critical charge current flow. Now, if we flip the sign of the DC current, we flip the sum of spin Hall effect generated spin current. Spin current flow direction is the same, but spin direction is opposite. So now we flip the free layer magnetization back to the original anti-parallel configuration. So we go to the high resistance state. And you can see there's a switch loop demonstrated in the experiment. So in this geometry, we already see that it's already separated the reading and the writing paths compared to the spin transfer torque. And also in principle, this spin current generation is not a monotonic function of the charge current. So if we can find a very good material or some interesting new mechanism to generate the spin current, in principle, we just need a very small electric current to generate quite a large spin current. The spin current then can flip the magnetization. And but there's already some limitation, as you see from this cartoon, that when we apply electric field, because of the geometry and the symmetry, we can only generate the spin current in the with spin direction in plane, so in the y direction here. So if we have some if we have ferromagnets with out of plane magnetization, we won't be able to flip them deterministically. This is actually our main motivation to study the new system, new materials. So let's go over the general form of the spin-orbit torque very quickly. So here is our conventional bilayer geometry again. We will see that many, many times, just bear with me. So we will have electric field in the x direction, just for the illustration purpose. And because of the stacking of heterostructure, the z direction is also, the z direction is z2 minus the mirror symmetry is also breaking. Of course, the electric field already breaks the x2 minus x direction. So in this heterostructure bilayers, we only have one effective mirror symmetry left, this y2 minus y symmetry. And this mirror symmetry dictates the form of torque. So basically, without doing anything from the symmetry argument, you already know that there are only a certain form of torque which are symmetry allowed. The two well-studied ones are written here. One is the field-like torque, which is a time reversal odd one. It has a form of y cross m. Y is basically the effective magnetic field generated by so-called Rashba model. So please check out this classical reference, seminal reference, talking about how to generate field-like torque from the Rashba model. This field-like torque will try to move the magnetization in a circle or precision here. And there's another well-studied form, dampinglike torque, which has the form of m cross y. If you do the vector algebra here, it will try to pull the magnetization into the y direction. And from that, you can also see it is time reversal even. And there's a Kubo formula to calculate that. Kubo formula, of course, can also calculate time reversal odd one also. Here we focus in this expression, we just show that there's an interband contribution, just like anomalous Hall effect analogy here. So besides these two, there are other general form of spin-orbit torque, which are in higher order of magnetization. We will not go through that, but there are some excellent reference you can look them up. But we will encounter these higher order terms later in the first principle calculations. But for most purpose of this talk, these two are the dominant form. And we will actually focus on this time reversal even torque more, because this dampinglike torque can switch the magnetization, as we show in the previous slides. Okay, so that's now looking at this geometry, and imagine we have a similar setup where electric field in the x direction, stacking in the z direction. So there is a mirror symmetry in the y direction. So when the magnetization is not in the high symmetry y direction, the torque will try to pull the magnetization into that direction. So you should try to pull it down until the magnetization is aligning with the y direction. In that case, there's no torque anywhere because of the symmetry. So that's the a very big or large limitation in this heavy metal non-magnetic bilayer. So heavy metal ferromagnet bilayer structure. That's we cannot actually switch the magnetization into out of plane deterministically. And there's a huge motivation here to try to switch the out of plane magnetization due to the higher density and efficiency in these magnets with perpendicular anisotropy. So the way to do that is to break this mirror symmetry as we show in the previous one. So there are many ways to do that. For example, Vivek Armin in the previous talk showed that we can add another ferromagnet layer in the bottom. In the tri-layer setup, basically you break any existing mirror symmetry in the system. And you can also add anti-ferromagnets. People talk about this exchange bias idea. But all these ideas have one, or you can actually apply external field, but that's even less desired because we want a field-free switch. For the tri-layer setup, the only problem or complexity is you add another layer, and people already talk about whether it's coming from interfacial or bulk. There's a constant argument about these things. When you add another layer, you just make the whole thing more complicated. So there's a simple way to do this, to break this impedance symmetry is to find a material, for example, find a new heavy metal or substrate with no impedance symmetry breaking. That's exactly what this experiment from Cornell group has shown. Instead using some large heavy metal such as platinum to be a spin Hall generator, spin Hall effect generator. They actually look at these new two-dimensional materials, 1T prime tungsten ditelluride in their experiment. And so this 1T prime tungsten ditelluride is a two-dimensional material. One of them there's a big family of two-dimensional materials, but it is one of them, and it's very interesting material for its own purpose. In the three-dimensional bulk form, this 1T prime tungsten ditelluride is predicted to be a type 2 well-signed metal, which already tells you that there are interesting topology in their band structure. And in the one model layer limit, this thin film of tungsten ditelluride is also a quantum spin Hall insulator. If you actually dope the system, you can actually get the superconducting out of it. So it's quite interesting. But for our purpose of using it as a substrate to generate spin currents, or for this bilayer setup purpose, we only need to worry about their symmetry. So in this system, we only have one mirror symmetry, is in the x direction, x2 minus s. As you can see, the tungsten and tellurium atoms go back to themselves after you flip the x2 minus x. In the y direction, there's no such mirror symmetry. There's only a glide symmetry. But when you put the ferromagnets on top of that, the glide symmetry is just broken. So also the previous speaker, Safir and Guimares, actually Guimares is the author on this paper. They already talk about these new materials and how it can generate the unconventional spin-orbit torque or spin current in the experiment. Please check out their previous talks. So again, this is a geometry, cartoon geometry for this bilayer structure we are looking at. So we have a conventional one, platinum and ferromagnets. When we apply an electric field in the x direction, and let's assume the magnetization is also in the x direction. So we generate a spin current. The spin current will exert a torque on the ferromagnets. So we will have a dampinglike torque in the parallel direction, input direction. So that's tau parallel means. So in the tungsten ditelluride case, because we break the y2 minus y symmetry, when we apply a electric field in the x direction, we can generate a spin current, conventional one with input spin direction and also out of plane spin direction. So blue arrows are flow. Blue arrows denote the flow direction. These black arrows means the spin direction. So this spin current can then exert a torque on the magnets. So the perpendicular one or out of plane one will exert a torque, damping-like torque on the ferromagnets to the perpendicular out of plane direction, and the in-plane one will just get an in-plane damping-like torque. So this is their experimental data. They demonstrate that they use a spin Hall ferromagnetic FMR technique to see that indeed we see a new signal when we change the substrate from platinum to the tungsten ditelluride. And another thing is you have to apply the electric field in the A direction. I will talk about that a little bit later. So in this control or compare experiment, they see that this anti-symmetric potential readout, they see a new terms. You have to change to convert from this VA experimental readout to the torque we care about. You have to divide by this common sine 2 phi factor. So by doing that, we see that there's a new constant out of plane torque in this tungsten ditelluride Permalloy structure. If you apply the electric in the experiment, when they apply the electric field along the A is X here in this cartoon. So when they apply the electric field in the Y direction, because of the mirror symmetry in the X direction is still preserved, they don't see this unconventional constant out of plane torque. So this brings up our numerical calculation of this new system, and also our main motivation to look at these things. So we perform our first principle calculations, starting from getting a sort of relaxed heterostructures. But because of the limitation of the computation time and the cost, we cannot go very large unicell. So in this simulation, we are having a hard time to get the reasonable relaxed structure with the cobalt and PMD. So keep in mind that this is not the real heterostructure. We don't believe it's the right real one compared to the experiment. Especially the experiment does not use cobalt, they use Permalloy because you can just spatter them on top of that. And after getting this relaxed structure, we do the conventional or standard 1 near 90 procedure to interpolate or extract the effective atomic orbitals to describe the ab initio Hamiltonian. And with this tight binding model, we can get all the information about different angular momentum reservoirs in this system. And then we we can just use the Kubo formula, standard Kubo formula to calculate the torque. We calculate both timers, so even one and the odd one. This kind of procedure is sort of standard in our community now. There are many references. These are three the one I found out were useful. So please check them out if you want to look at all the experimental details. In all these references, they focus on the conventional heavy metal with ferromagnets one. But we are looking at the new material with impedance symmetry breaking built in the system. So this is the first takeaway, the result. So remind ourselves about the geometry again, because we will use some notation here. So I don't want to lose all of you by just looking at some complicated graph. So apply the electric field in the X direction, which is the mirror symmetry direction. And in this tungsten ditelluride cobalt heterostructure, we know that both perpendicular and the in-plane spin current can be generated. These two, in principle, can flip the damping-like torque, can exert the torque on the top cobalt layers. And this is a result the resulting magnetic sphere, a magnetic angle dependence of the torque. So we plotted the torque on this magnetization sphere, theta and phi angle. Theta is the magnetization with z direction, phi is the impedance direction. And the unit is in this h bar over 2e per ohm per centimeter. And the color actually here indicates the absolute strength of the torque. And we see that for the time ratio even parts, we also interchangeably call it dampinglike torque, even though it can have higher order terms. So we see that the torque does not vanish at this high symmetry direction when the magnetization is along the y. We know from the symmetry it's not allowed in the conventional system. But here, because we break the mirror symmetry already, we are allowed to have an out-of-plane torque. So we see that the fixed point is not in some high symmetry direction in this magnetization dependent sphere. It's actually in some arbitrary direction along this YZ line. So if you change the atom or you change your pseudo potential you use, just change a little bit in your first principle calculation, you can get a fixed point to some other place. So this is not something from symmetry. This is just coincidence or model dependent, if you like. So this dampinglike torque already tell us that we can flip the magnetization into the out-of-plane direction deterministically. So this already tells us we can use it as a spin-orbit torque mechanism to flip the magnets with perpendicular isotropy. So this is the time ratio out part. This conventional has this field-like torque. We also have that, but there's also higher order contributions, which are not of interest in this talk. But we see that for this field-like torque, we see unconventional behavior also. We see that in the high symmetry y direction, there is still a torque, even though it's small, but it's still non-zero, which is not allowed in the conventional one. So now let's switch the electric field direction into the y direction, just as the experiment has done. We know that when we apply electric field in the y direction, the high symmetry, the mirror symmetry x to minus x is still preserved. Then we are expect to get the conventional result with vanishing torque at high symmetry x axis. And indeed, we get the vanishing torque for both even and the odd part of the spin-orbit torque. So in this time ratio even part, it's not dampinglike anymore because it has some higher order contribution, the phi dependence. So it's weird. It's a weird form, but that's not what we are going to go through in this talk. But it's possible. It's symmetry allowed. So when something is symmetry allowed, I'm not surprised to see it just appear. For the field-like part, the time ratio out part, this become very typical behavior, just a torque putting the magnetization along the high symmetry effective magnetic field x direction. So another interesting observation in the experiment is that in their samples, when they have when they do this experiment, they do this Scotch tape kind of technique. So they just use a Scotch tape to exfoliate the bulk tungsten ditelluride and then put the cobalt on top of that. Permalloy on top of that. So when they do this exfoliation, it's not necessary to get one single interfacial configuration between the TMDs and the Permalloy. In fact, they get two. So in our simulation, we also try to do that. Try to get two relaxed configuration where the interface between cobalt and the tungsten ditelluride is opposite in these two cases, which means the impedance breaking polarity Y is opposite in these two cases. And we expect that from the symmetry, the out-of-plane torque shown in this geometry will be opposite due to the nature of the symmetry. And it is indeed the case that, here we scan the magnetization on the impedance to make it simple. So we see that the out-of-plane one indeed flip the sign. But for the input one, it's coming from the polarity in the z direction or in the stacking direction, which is not a change in these two configurations. So we expect them not to be not to change too much. So, but in a realist, I mean, in an ideal system, where we perform all these first principle calculation, what we are doing is just change the sign of the electric field. But keep in mind that we do this realization in a not perfect condition where cobalt is not ideally to be opposite. So it still shows this strong opposite behavior. So which means the symmetry still mostly guarantee the results. So motivated by some other works to look at how disorder change the behavior. So we add a small on-site random potential in the cobalt layer, in the ferromagnet layer, with a range quite small here, minus 0.1 to 0.1 eV. So we want to see whether the number whether the out-of-plane dampinglike torque number depends on these different configurations. So here the right dots just show 40 different configuration of random potential, and we get different value of the out-of-plane torque. And the blue line is just the average of that. So from this calculation, we need, and also we do a scan along the chemical potential, which is a theorist trick. We can easily do that in the simulation, even though it's not something the experiment can easily do. But to do this, we can know the trend of the behavior rather than just looking at single points, which is not very useful knowledge. So by extracting the information from this calculation, we see there's a large error bar for the number we calculate. So it can be more than 50% in the perpendicular dampinglike torque. And also we compare with experiments, they show that they have a little smaller than what we have calculated. And these two numbers are all one order smaller than the conventional heavy metal platinum cobalt bilayer. So the important takeaway from this calculation, at least from my personal view, is that DMT is quite powerful. It's a quite powerful tool to calculate something. But these values from DMT calculation, they are so-called ab initio, but they depend on a lot of details. So they are not something you can, not some figure merit for the experiment to really to get. So for me, the more important thing I want to study is to find out why such a, to find out the microscopic source of this spin-orbit torque we see in the experiments, in the calculations. And the DFT framework have this wonderful advantage to do that. In the experiments, you may not access all the information underlying mechanism because of the limited experimental observations. So this jump to us the next one, the next takeaway. We're trying to find out the source, microscopic source of spin-orbit torque in this heterostructure. So just remind ourselves again, we have this framework of different angular momentum reservoirs, and the flow can occur in the different reservoir due to different interactions. So we have this spin Hall current flux into the ferromagnets. We can get the spin transfer torque. So we can also have the spin-orbit coupling generated spin current flow from these three reservoirs. And in principle, you can also study the orbital Hall current flux, which is not this talk's focus, but yeah, you can look at the previous talk from Dongwoo Go. He showed that we can also track that. And also this collaboration paper between our group and their group. And understanding these two different reservoirs, these two boxes, we already can understand what happens in these classical spin Hall torque, spin orbit torque experiments. So it's basically a box spin Hall generation, spin Hall effect in the this orange box, and then we plus this blue box, which is a spin transfer torque. we get the simple spin-orbit torque idea. So how about our calculation or our system with unconventional materials? Does this simple physical diagram still works, or the cartoon works? So we know that in the ferromagnet cobalt tungsten ditelluride heterostructure, we can also calculate the electric field induced spin current flux into the cobalt layer. And we can also calculate the torque on cobalt layer only. We found that the torque on cobalt is almost equal to the torque in the whole system. So which are saying that we don't have a very strong we don't have a strong magnetization in the tungsten ditelluride due to the proximity effect. So that's good. That's a simple. Let's make this picture simpler. So when we compare that for the parallel or conventional form, first we see that indeed the cobalt, the torque on the cobalt is almost the spin current flux, even though there are some differences. But in the near the Fermi level, it's almost overlap. So this is as expected, because in the experiments, they also perform the layer thickness dependence. They already see that this input part dampinglike torque is coming from the bulk spin Hall effect. So, but not for this perpendicular one, because in the layer thickness dependence, they don't see any bulky behavior, and it's not as expected, of course. And this is not as expected either from the symmetry argument, because the bulk tungsten ditelluride does not support such a perpendicular spin current flow, a uniform spin current flow. So, but in our heterostructure calculation, we still find out that the spin current flux is almost equal to the torque on the cobalt, even for this perpendicular out-of-plane torque. So this motivates us to answer, motivate us to the next part. So if the spin current is the major source of the spin-orbit torque, can we get rid of this heterostructure complexity just looking at this bulk material, tungsten ditelluride, like the platinum case? Can we just look at the bulk Hall, spin Hall effect and calculate the spin current there in the bulk, which is much simpler, and extract a number out and see whether this is a good figure of merit for experiment to try out. So this is our next part. We try to calculate this spin Hall effect in the bulk for this out-of-plane component, which is not a uniform one, it's actually staggered. Let's just go into the details right now. So, so here we ignore all the heterostructure in this part. So if you are lost in the previous two parts, it doesn't matter. You can still catch on this one. I hope I can convey this clearly. So without this is the conventional spin Hall effect in a material with basically every symmetry. It's an isotropic system still supports this spin Hall effect. So in this spin Hall effect, by the way, I changed the notation a little bit. So now I'm fixing the flow direction. So from left to right is always the black arrow is the flow direction, and from down to up is always in the same flow direction. So the spin direction has also to be changed based on the symmetry argument. So in the isotropic material, we have a continuous spin Hall conductivity. So the spin direction is perpendicular to both flow direction and input electric field direction. So here, this in the tensor form is yxz. Y means the spin direction is in y direction. X is the electric field direction. Z in the index is the current flow direction. So when we break the mirror symmetry, we are allowed to have this new form of tensor. This is sigma zxz component. So the spin current direction actually align with the spin current flow direction, which are not allowed in the isotropic material, but is allowed when we break the impedance symmetry. In this geometry is y2 minus y. But it's still uniform. So if you look at the flow from bottom to top, you see a uniform spin current flow just with the spin direction parallel with the flow direction. Now in the tungsten ditelluride, when there's a glide symmetry, which means that in the bulk, we actually don't have the unconventional form. So this glide symmetry requires the impedance symmetry breaking to be opposite in the tungsten ditelluride, but this doesn't affect the conventional YXZ form. It's still uniform passing from one layer to the other layer. So we have a uniform position dependence spin Hall conductivity. But for this out-of-plane one or unconventional ZXZ component where the spin polarization and spin flow direction along with each other, it will be staggered because the glide symmetry actually forbids the total spin Hall conductivity in the bulk. So we must cancel that. So we do this. So they arrange themselves to be staggered to cancel the total spin Hall conductivity. So layer one. So between the layer one, layer two, and between the layer one and the other layer two, we have the opposite side of the spin Hall conductivity for this one. So that's why you cannot easily calculate this one just by using Kubo formula for the conventional package, even in the 1 year 90. So you have to do a little bit. You have to use you have to trouble yourself a little bit to get that. But that's not. If you are interested, you can ask me later. I can explain how we calculate that. But here's a result from the first principle calculation. First, we do this 1T prime tungsten ditelluride bulk calculation. We see a uniform spin Hall conductivity in a conventional form. This agrees well with the previous first principle calculations. And the second one is the new one we found out. There is a staggered spin Hall conductivity depending on which layer you are looking at. So we see that stagger can be as large as 20 h bar over 2e per ohm per centimeter. This is in the same number scale, quantity scale of the spin-orbit torque exerted in the experiment and also in our numerical calculations. So this actually double confirm that the spin Hall effect can be the source of the spin-orbit torque in the experiment. Now this number is a little bit small if you are from the heavy metal platinum case. So you see, why do you care about that? The reason we care about that is with this framework, we can easily find out other materials in the, it's basically chemistry job now. So we just look at the periodic element tables. We find out some heavy spin-orbit couple elements, and we find the proper space groups symmetries to allow this staggered behavior. The key point is we in the individual atom or in the individual layer, we only want one mirror symmetry. For example, X to minus S. All other mirror symmetry must be non-symmorphic in the sense that it does not require each layer to be highly symmetric. So for example, we found out this orthorhombic light telluride semiconductor. In the conventional form of this small bandgap material is not in this orthorhombic phase, it's in the rock salt phase. But this phase is still achievable in the experiment by doing the pressure. But this phase allows us to have this staggered spin Hall effect. So as a proof of principle, we just show that as an example. So here we actually have 4 layers of different atoms. And if we perform the similar position dependent spin Hall conductivity calculation from first principles, we scan the chemical potential. Here we have to go below the Fermi level because this is a semiconductor. So we see that quite large spin Hall conductivity for the conventional YXZ form. And it's not necessary to be equal between 0, 1 and 0, 2, but the symmetry actually requires layer 1 and layer 3, layer 2 and layer 4 to be equal to each other. So the number is quite large. If you remember, this 1000 number is close to the platinum, which is a figure of merit in the spin Hall effect field. So what about this unconventional one? It's expected to be staggered, and it is indeed staggered in the calculation. And because of symmetry, actually there's no spin Hall conductivity in the layer between layer 1, layer 2, between layers 3 and layer 4. But there are staggered between layer 2 and layer 3 and the layer 1 there here in the Z4 and Z2. So they are staggered, and more importantly, they are quite large. They are in the range of more than 200 or even 300 h^2e per ohm per centimeter. This is already in the range of effective spin Hall conductivity regime. And if you want to use the figure of merit spin Hall angle, this is doped semiconductor, so you can expect quite a large spin Hall angle if you like. So this brings us to our conclusion. So I hope that I convey the two important takeaways in this talk. First, we demonstrate the first principle calculation. In the first principle calculation, the spin orbit torque with the out-of-plane component can be efficiently generated in the crystal with reduced symmetry, such as tungsten ditelluride. And we found out that the spin current flux from the tungsten ditelluride to the cobalt or ferromagnets is the main source of the spin orbit torque. So we look at a bulk staggered spin Hall effect in the tungsten ditelluride, find out this indeed can generate the considerable spin current. We also propose some new materials, and this paper will be published shortly, so you can check out, and if you like, you can do your own chemistry finding to find a better material. And also I want to acknowledge all my collaborator at NIST and the collaborator at Germany and Korea. And thank you. Also acknowledge the funding through the University of Maryland. Thank you so much for your attention. I'm happy to take any question you have.
Thank you very much for the interesting talk. This talk is open for questions. If you're in Zoom, please use the raise hand function. If you don't know how to do that, you can send me a private chat. And if you're on Twitch, just feel free to type your questions in the chat box, and I'll read it for you. The first question, Ren, please go ahead with a question.
Hi, hello. Hi. Thanks for the very nice talk. So I have a simple question. So maybe this is because I missed some part of your talk. So the spin Hall effect in your calculation is independent of the angles between the currents and the crystal direction, right? I'm not sure if I can understand that. So only the perpendicular part, which is obviously depends on the angles, but the spin Hall component is independent of the angles in your calculation, right?
You mean the last part, right? The bulk calculation?
Yes.
Yeah.
I mean the in-plane angles between the applied current and the crystal direction. So
yeah, it depends. Here
it depends. Okay.
Here, yeah, of course it depends. But here you so here in all the system we study is orthorhombic, which means A, B, C, and X, Y, Z are on top of each other. But in principle, you can calculate the instead X, Y, Z in the non-orthorhombic system. You can study A, B, C, B, C, A, all the things. And then you do the crystal vector conversion to Cartesian coordinates, and you can get whatever direction you like.
Okay, I see.
Yeah.
Okay, thank you.
Yeah, but and yeah, and this is a very good point. Here, YXZ is not equal to XYZ, and also not equal to ZXY. You're right. This is only YXZ. If I change the indices, number will be changed, but behavior is similar. Yeah.
Okay.
So for example, XZZ is still staggered. Yeah. So yeah, XZZ is still be staggered, but YXZ is still uniform.
Oh, I see. Okay, so only YXZ component is quite independent of the azimuthal angle, but not the other components.
I'm not sure what you mean by azimuthal angle here.
Oh, maybe we can discuss later. Okay.
Okay, no problem.
Thank you.
Is there any other question? I just want to ask a quick one. So in your simulation for the heterostructure, do you take into consideration the spin-orbit coupling in cobalt?
Yes.
So that's already
Yes.
involved. So that means
Yeah.
when you
Go ahead.
So sorry. So but when you compare that with the calculation of the spin current, the bulk spin current calculation, that does not include the orbital Hall effect, does it?
No. It's just us. What you mean this calculation or
the QS? I think the tall cobalt must include everything. QS, which is the bulk spin current generated.
Yeah, indeed. There's in principle a QL part, but if you compare that, that would be the difference, right? But that's quite small.
So it's small. Yeah. I see. Yeah. So that means in this system, it's unlikely because QL is eventually the torque due to QL is going to depend on the spin-orbital coupling in the ferromagnet.
Yeah.
But that seems to be a minor effect.
Yeah, very good point. In fact, we were expected to find something more complicated than that in this new system because this is not platinum cobalt, which we know that is spin Hall. So we are actually motivated we work on this framework. We try to see whether we can something more interesting, more novel in a sense. Turn out to be not. But it's not bad. I mean, it just makes things simpler, so you can just do simpler things rather than complicated things. But sure. In this framework, you can, as you said, in our calculation, indeed we have other components, but for the purpose of the simplicity and for the talk, I just ignore all of them. Yeah.
I see. Sure. Thank you. And Hua Chen, please go ahead with the question.
Thanks, Fei, for the nice talk. So it's just a technical question for the last part. Did you use the one-year interpolation to calculate the spin Hall conductivity?
Yes.
In doing that, do you have to use the symmetry adapted one-year function or didn't?
Yeah, very good point. 1-year 90 has this problem of symmetrizing itself. So we use so-called TB models. It's a package from from Europe. So they have a Python open sources package tell you how to. They basically use the Python package to do all these symmetrized process for the real space 1-year 90 Hamiltonian. Yeah, we have to do that to get. Otherwise you won't get exact stagger or exact uniform. You will get something weird but close to that. Yeah.
Thanks.
Kirill, please go ahead with your question.
Yes, thanks. So a question about this staggered spin current that you showed. Mm-hmm. So if you have this in a heterostructure, so if you interpret the current as having an interfacial origin, then it's straightforward. But if you want to talk about the bulk source, then so normally if you have a conventional material, so you need a certain thickness for the source layer to generate spin current. So with the staggered one, how does it work?
So it's still we are now trying to argue that the experiment must be from bulk or interface because we are now capable to do that, have that conclusion. This staggered thing is motivated by the observation that spin current can still be a major source of the torque rather than some complicated interfacial hybridization. So then we ask ourselves, I mean, of course, interface can also generate spin current as Vivek showed before, but we want something even simpler, right? We consider if we have a bulk material, can we have this kind of new spin current direction? And it's allowed by doing this stagger.
Sorry, I understand that. But if you're talking about bulk, you also need to have some analog of the spin diffusion model, right? So if you just calculate the bulk spin Hall current, you can't just take that as the value for the bilayer. If it's thin,
it won't be the bilayer. Right? Yeah, yeah, it probably, so in the experiment, they also have multi-layer, they don't see, so this stagger also is kind of qualitatively explain why in the experiment, they don't see increase of out output torque, because stagger does not add up just like uniform one. Like you said, even I do a 3, 4, 5, 6 layer, they always just alternating the sign rather than increase their magnitude. And yeah, I expect there may be a very small short spin diffusion lines. Yeah.
Yeah, but do you think if you take, so you're calculating these currents in an infinite sample. So if you now take a finite thickness with only a few layers,
yeah,
and you cut it, right? So it's
yeah.
a certain thickness. Is it going to be
Yeah.
suppressed compared to the bulk value as a non-staggered one would if your thickness is smaller than the spin diffusion length, or not in that case?
I don't think so. Actually, I think in the other paper, in the new experimental paper, they have also done the PbTe calculation, but for 3 layer, just like you suggest, the odd layer of spin, odd layer of tungsten ditelluride, maybe molybdenum ditelluride, the magnitude is similar. So you don't see, so it's not like conventional one, it drops, but it's similar, yeah. Somehow this stagger does not depend on the layer too much.
Okay, thank you.
Yeah.
Do you have any other question? Okay, if there's no more question, I want to thank the speaker again for the very interesting talk, and I want to thank everyone for participating.